All right, so to do an hypothesis test for means, we start our hypotheses in terms of mean, in terms of the population mean. Either you can write mean or you write the Greek letter mu as the parameter. We check the independence and normality conditions. So, again, random sample, or at least random assignment, and then not too much skewness for the sample size. The standard error is S over the square root of n to calculate the standard error. From there, we'll take the test statistic, which is point estimate minus the null value over standard error. So it's the same calculation, except now I call it a t instead of a z-score. Once we have our test statistic, we'll calculate the two-tail p-value using the degrees of freedom as n minus 1. That is the sample size minus 1. For TI calculators, we'll use the TCDF, absolute value of that test statistic. That is, if it's a negative score, drop the negative sign. Then the upper bound, 999, is more than sufficient. And then the degrees of freedom, times 2. For Casio calculators, use the TCD command. And then the same information. We'll compare the p-value to the significance level, which for the most part we'll use 0.05 as our boundary, and we'll make a conclusion. If the p-value is less than that significance level, then that would be considered enough evidence to reject the null hypothesis. If the p-value is greater than or equal to the significance level, then this would be considered insufficient evidence to reject. So we'd fail to reject. Okay, so for example, is the typical US runner getting faster or slower over time? We consider this question in the context of the cherry blossom run, comparing runners in 2006 and 2012. Technological advances in shoes, training, and diet might suggest runners could be faster in 2012. An opposing viewpoint might say that the average body mass index on the rise, people will tend to run slower. And in fact, all these components might be influencing the run time. So, the average run time for all runners who finished the cherry blossom run in 2006 was 93.29, which is 93 minutes and about 17 seconds. We want to determine, using data from 100 randomly selected participants in the 2012 cherry blossom run, whether runners in this race are getting faster or slower, versus the possibility that there had been no change. So, in terms of hypotheses, our samples for 2012, we know the true average for 2006. So, what we want to know is whether the 2012 time is equal to the 2006 time, or not equal to. So, the mean for 2012 is equal to 93.29, which was the mean for 2006. The alternative is that the mean for 2012 is not equal to 93.29. It may be higher, or may be lower, but it's something different than 93.29, which was, again, the mean for 2006. The data come from a simple random sample from less than 10% of the participants, so the observations are independent. And my sample size is 100. You can see from the histogram, may not absolutely perfect, but it's more or less unimodal, symmetric, kind of. Certainly a sample size of 100 is more than large enough for this. So the graph shows little to no skew, and even if skewness was present, a sample size of 100 and the central limit theorem guarantees normality. Okay, so let's get to the rest of this. The sample mean and standard deviation are 95.61 and 15.78. And recall the null value was 93.29. So what is the p-value? Well, point estimate is 95.61. That's the sample mean. Standard error would be 15.78 divided by square root of 100, which square root of 100 is 10, so I move the decimal one place to the left, 1.578. The test statistic you'd find by taking the point estimate, 95.61. Oops. Try it again. 95.61 minus 93.29 in parentheses, and then divide by the standard error of 1.578. So the test statistic is about 1.47. Oops. Degrees of freedom, sample size minus 1 will give me 99 degrees of freedom. And then the p-value, I would choose TCDF, so option 6, 1.47 to 999, 99 degrees of freedom, and then times 2. And I get a p-value of about 14%. So 0.145. So this is larger than 5%, so we should fail to reject the null hypothesis. There is no evidence that the average time has changed between 2006 and 2012. It may be higher, may be lower, but based on my sample, I can't tell.